Hi all, thanks for coming to the seminar that will be presented by Praveen. So for those who don't know Praveen, he's a doctoral student in the lab towards the end of his program. And so he's going to be presenting his work on expression or emotion recognition. So please go ahead.
Yeah. Hi everyone. So I'm happy to present my work on attention models for audio-visual fusion and dimensional emotion recognition. So this is the outline of my presentation. So I'll first briefly introduce what is dimensional emotion recognition, and I will present some of the models I explored in this work, and finally with conclusion. So dimensional emotion recognition. So dimensional emotion recognition is basically the task of recognizing emotions on the two-dimensional space of valence and arousal. So basically valence means the range of emotions from being very sad and depressed to it's like very happy. And arousal, it basically reflects the intensity of emotions from being very passive to active. For example, we can see here it's being calm and very excited. So it's like whatever the emotions we can have, everything can fit into this space. So it's basically it's recognizing the emotions in this space. So audio and visual are the major it's like modalities which have been explored for many applications, including emotion recognition. And in audio and visual modalities, they have this complementary relationship. So which means that, for example, if you take some of the video clips, we might be having rich visual information, but we may not have rich audio information, and vice versa. So how we can be able to capture this complementary relationship across the audio and visual modalities? So by effectively fusing the audio and visual modalities, we are expected to have like improved performance when compared to like unimodal approaches. And yeah, so this is the way that how we extract the facial clips, and we have this this audio channel, and we feed that to our emotion recognition block, and we get the output. And these are some of the challenges for audio visual fusion. And extracting efficient audio visual feature representation is one of the fundamental challenges of audio-visual fusion. And it is also important to effectively like exploit the complementary relationship across the audio and visual modalities. And in facial expressions, we have like wide range of variations being it might be due to pose and like resolution, illumination, and things like that. So the system has to be like robust to it's like all these edge cases. And similarly, for vocal expressions, we have different, we have like wide range of variations in terms of noise and identity bias and things like that. And these are some of the approaches for dimensional emotion recognition. So Rajasekar et al. Is one of the early approaches that used deep learning models for dimensional emotion recognition, where basically they have used like 1D CNN for audio and resonate 50 for video, and used LSTM for prediction. And Shoniol is one of the recent approaches where they have used like knowledge distillation for visual modality, and spectrograms with 2D CNN for audio modality, and they also used LSTM. And recently, so recently, Rajasekar et al. They have explored different fusion mechanisms, like including self-attention. And this is one of the recent approaches where they have used transformers to it's kind of exploit the cross-modal association across the audio and visual modalities. So these are some of the limitations of the existing approaches. So if we see that most of the approaches, they focus on modeling the intra-modal relationships using LSTMs. And And the inter-modal association across the audio and visual modalities, it is not effectively explored in the literature. So, though there are few attention models which have been recently explored with transformers, they do not effectively capture the cross-modal audio-visual relationships. And the semantic relevance across the audio and visual modalities are not effectively explored in the literature. So the semantic relevance means we have like intra-modal association as well as inter-modal association. So we need to like efficiently, it's like leverage, it's like intra and inter-modal association, so have an efficient audio-visual fusion system. So this is my first approach, cross-attentional attentional audiovisual fusion. So this is the framework of our approach. So basically we have the video and we separate the video to visual and audio stream, and we do some pre-processing to like extract the facial clips and spectrograms for audio. And this is the it's like the deep models we use to it's like extract the audio and visual feature vectors. So these features are trained independently in order to extract the feature vectors. And finally, after extracting the feature vectors, we feed that to our fusion model in order to have the final prediction of valence and arousal. So this is the visual backbone we have used. So I3D is the one which we have primarily explored in this work, and where I3D is basically it's used for action recognition in videos, and I3D is basically it's kind of inflated version of 3D models where we can be able to like leverage the existing pre-trained models with 2D CNNs for 3D CNNs. So we feed the facial images to our model, and we get the visual feature vectors. And similarly for audio, we use spectrograms, and so basically we have the spectrograms for each clip, and we feed that to 2D CNN model to extract the audio feature vectors. So this is the fusion block where, as I mentioned, that we feed our audio and visual feature vectors to the fusion model. So as we see in the fusion model, we have this this correlation matrix. It's like across the audio and visual feature vectors. So we can see in these equations that basically we estimate the correlation across the audio and visual feature vectors. And so as we can see that every element in Z, it basically gives a semantic measure of relevance across the audio and visual feature vectors. And these are the cross attention weights, where basically it's kind of we apply softmax on this matrix, and we obtain these cross attention weights. And these are the attention maps which we get from the attention weights. So it's like after we complete the attention weights, we use the attention weights to it's like estimate the attention maps, and then finally we get the attended features using these equations, where we basically add the attention maps and the feature vectors in order to have the final attended features, which is further concatenated and fed to fully connected layers for final prediction of valence and arousal. So we have validated the proposed approach on RECOLA dataset, and RECOLA dataset is the one which has been widely used in various challenges like AWEC 2015 and 2016. It has 18 subjects, in which 9 for training and 9 for validation. And CCC is one of the, it's like evaluation, it's metric which has been widely used for dimensional emotion recognition. And this is the ablation study that we did with the RECOLA dataset. So we did a few experiments with different fusion strategies. For example, we tried 2D CNNs as well as 3D CNNs with feature concatenation and LSTM and even self-attention. So the proposed approach was able to perform, it's like much better. It's like when compared to existing approaches. And these are some of the visual results. So as we can see here, so we are able to track the ground truth here, where it's like, even if you can see here, like we have this small peak kind of thing, we are able to even capture that one. And if you see here, like we have some, it's like in spite of not being able to have the frontal face of the image, but still we are able to track the ground truth. So and if you can observe these plots, that it works. It works efficiently for it's like valence. It's like when compared to arousal. And these are some of the results with the state of the art. So as we can see, we are able to achieve some good performance when compared to state of the art. And yeah, and we further extended the approach and we proposed a joint cross-attentional model. So basically the framework remains the same. The only difference here is the fusion block. So as we can see, this is the new fusion block, where in this fusion block, we have this new joint representation. So if you look at the model which I explained before, basically, if you look at the correlation matrix, it is across the audio and visual feature vectors. But in this model, we do that it's like across the visual features and it's point representation here. So by doing this kind of correlation across the visual features and point representation, we can be able to exploit the intra-modal association as well as the inter-modal association. So and then we use the we use the attention weights here, and finally the attended features, which is finally used for the final prediction. So you can see some of the equations here that so as we see here, so here the new it's like in this version we have this say which is the which is like audio visual feature representation. So it basically gives you the inter and intra-modal correlation. It's like across the modality as well as within the modality. And same thing we compute for visual modality also. And this is how we estimate the joint cross-attention weights. So basically we have these weights which are like learnable, and we estimate the attention weights. And after that, we have these attended features, which we basically, after estimating the attention weights, we just add that to the actual feature vectors, and we get the attended features. So yeah, and we have done some experiments with AffWild2 dataset. AffWild2 dataset is one of the major one. It is the largest dataset in the field of affective computing, and it's a wild dataset. It's captured from like YouTube, and it has 341 training videos and 71 validation and 152 as testing videos. Yeah, and we also did some experiments with RECOLA as well, and these are some of the results which we explore different fusion strategies. So we have explored almost the same set of experiments which we did before, simple feature concatenation and LSTM. And this is cross-attention, which I just explained before. And and these are the results with cross-attention. And after introducing the joint representation, where we capture the intra-modal association as well, we can, like we showed some improvement here. And we also explored with multiple backbones of each modality, where we use like I3D and R3D for visual modality, and even 2D CNN. And we showed even slightly more improvement than the normal one. And yeah, and we did the same series of experiments with AffWild2 dataset also, and we got the same improvement with this dataset also. So as we can see here, this is the result with this model, and it's better than the existing ones. And this is with comparison to state of the art and RECOLA dataset. And as we see that we are able to achieve quite good improvement with this new model of joint cross-attention when compared to like simply doing a cross-attentional model. Yeah, and we also validated the approach with AffWild2 development set as well as test set. So we can see that the results are consistent in both the partitions, and yeah, so these are the results which was submitted to challenge in CVPR workshop, and so these are our results. Yeah, so these are some of the visual results. So as we see here, CA is basically a cross-attentional model, and JCA is a joint cross-attentional model. So as we see here, that we have this guy like laughing here, and we have like more attention weights for this frame. And if you see simple cross-attention, it is not able to capture that one. So the first row is like audio attention weights, and this one is like visual attention weights. And similarly here also we can see the same trend, that we have like a bit more attention weights here. We can see some more results here. So if you see here, so here we are able to have like higher attention weights for visual modality, and yeah, and even for here, as he's speaking something with some loud, so we can see in spectrograms also, like it has like a bit more higher attention weights. And if you see here, like though he didn't have like intense expression in cross attention, it shows as intense expression, but here we are able to effectively capture by inducing the it's like intra-modal association also. Yeah, so this is one of the examples which we can see clearly that if we look at these clips, that we don't have much visual information available because of poor resolution and blur and things like that. But still we have like rich audio information. As you see here, like she's like yelling and she's like doing something. So we have like maximum attention weight for audio, but for visual we don't have much here. So yeah, so it is able to like effectively it's like exploit the like inter-modal association. And yeah, so these are some of the visual results for valence and arousal, and we compared it with our previous cross-attentional model, and we can see that we are able to achieve better results and like in terms of this model, like when compared to a cross-attentional model. And this is our recent work, recurrent joint attention with LSTMs. And so here, the new thing that we did is like we tried it's kind of recursive training, where we explored like LSTMs to capture the intra-modal association, in addition to the joint representation, and in addition to the joint representation we have in the fusion block. So this is the fusion model. As we see here, that the attended features are again being read here. So it's a kind of recursive training where we train the features in a recursive way, and we also use it's like LSTMs for capturing the intra-modal association of individual modalities, and as well as the combined representation. So the major difference here is, if we remember the equations that I just showed before. So in this model, we like instead of having parameters, actually we reduced it here. So for example, if you see this equation here, like we have 2 here, it's like WA and CA, but in this model we merged it to have a single parameter. And second improvement is like, as I just mentioned, that we use like recursive training, where we use the feature vectors of the previous recursion, and we add that to the existing one, and we train the model. So these are the new improvements. And in addition to that, we have also like explored LSTMs for modeling the intra-modal association within the individual modalities, as well as the combined representation. So these are some of the results. This is the ablation study we did with AffWild2 dataset. And so basically what we did is, first we conducted some experiments without using LSTM to understand the impact of LSTMs in this model. So as we see here, like it's like without using LSTMs, and these are the results. And it's like and in this case we just use LSTM only for it's like individual in terms of audio and visual modalities, but we don't use like LSTM in capturing the intra-modal association of audio visual representation, and we got some improvement. And finally, we use LSTM for individual modality as well as combined representation. And finally, like we got even some more improvement by using LSTMs in both the cases. And we also tried with different number of iterations as we do. It's like recursive training. And these are the results with 2, 3, and 4. And we got best results with 2. And what we have observed here is, like, as we increase the number of iterations, it seems the performance actually goes down. And the same trend we can observe in test results also. So it can be attributed as a regularizer, you know, like where it improves the I tries to improve the ability of the model. It's like a bit more generalization ability. And these are the results with state of the art we have for validation set and for test set. So we are able to get good results. So as we see here, so this is the cross-attentional model, which is the first model I explained, and this is the joint cross-attentional model, which is the second one. And this is the latest one, which is recursive joint cross-attention plus LSTM. We can see that we had significant improvement with this new model. And we can see the same trend in test set results also. Yeah, so to conclude, basically, we started off with the motivation to answer, to understand how can we effectively capture the intra and intermodal associations across the audio and visual modalities. And we proposed a cross-attentional audio-visual fusion. And then we further extended the approach by deploying joint representation to capture the intra-modal association also, in addition to intermodal relationships. And recently, we further improved the model by using recursive fusion and LSTMs. And yeah, and we did extensive experiments on RECOLA and AffWild2 dataset. And we also did some more experiments with private dataset also. And yeah, so yes, if you have any questions, you can ask me.
Thanks, Praveen.
Thank you so much for listening.
Thank you. Are there any questions from the audience or from the online audience? Are there any questions from the online audience for Praveen? No, everyone's quiet. All right. If not, I can ask a question. Is your microphone on?
Yes.
Okay.
I think it's much.
Or maybe I should stay here and talk. We don't. So my question is, so you're working with arousal valence, right?
Yes.
So you're producing. So do you always need two models to produce arousal valence, or can you combine them somehow?
Yeah, that's a good thing. Yeah. So initially we used to do experiments with individual models, but recently we started doing like as it's like one model for both valence-arousal, and it actually it works even better because it adds to some extent to some sort of like regularization, because we are doing multitasking. So it actually it helps in improving the.
So it's some sort of a joint representation.
Yeah. So we use the same features, and with the it's kind of multitasking with valence-arousal, and that actually improves the performance.
Okay, and that simplifies quite a bit.
Yeah, it's
another question I had was kind of the same type of question in the sense that, so you're working with arousal valence, but which is a very complicated problem, you know, and a lot of researchers are working on that. But if you had to, for example, produce intensity levels like pain level, or fatigue, or what would you need to do? Can you use the same model without retraining, or do you need to retrain, or?
Yeah, I think we have to retrain the fusion block. Okay, we have to retrain the fusion block, and as I mentioned before that it works pretty well for valence. So valence is basically the wide range of variations from being very sad to happy, and arousal is basically its kind of intensity. So in terms of intensity, it's not that good. So maybe for pain intensity, we still get some good performance, but we can explore that. But I think for valence, it works much better. So compared to like arousal. So, yeah. But still, we can explore that for pain intensity. But the only thing is like we just have to retain the fusion model with pain intensity ones.
Like a fine tuning.
Yeah.
Okay.
Yeah.
So that means like if the task space is reduced, right? You just have one condition of pain, and then just the target is to vary the intensity. So do you think that it becomes more easy?
You mean
So here you have
pain
balance,
levels?
and at the same time, you also have to find the range of valence. At the same time, you have to find the intensity of each of them.
Right.
So the space is more, right?
Yeah,
So
right.
task space is bigger.
Yeah.
Then what Eric told is that like you just want to condition it just for one certain task, like how much pain
Right.
is getting induced in terms of intensity.
Yeah.
So the task space is getting reduced.
Yeah.
The question is like, if you want to adapt the model that you have now for this task,
Mm.
and you don't need to change the architecture, right? You basically just retrain or fine tune the fusion model and the task.
And final
fully
modulation.
connected
Fully connected. That's true.
My question, another question is like, when you is there any what is the frame rate of the results? How fast?
Frame rate of video.
I mean, you do it based on each frame or how fast?
It's for each clip. It's for each clip.
So the prediction is actually one prediction for the whole sequence.
No. It's for each frame.
Yeah.
Basically, what we do is we do the estimation of each clip, and the last frame will be associated with the label of the clip. So that means that, for example, so in this case, we do prediction for every frame, okay? But then the thing is like we use, for example, if the sequence length is like 8 frames, so it's like we estimate like valence and arousal for 8 frames, and we assign the label to it's the last frame of the clip. So like that we do it for every frame. So for example, if it is like 15th frame, we use the frames from maybe 7 to 15, and we get the prediction that is assigned to like last frame. So we shift the clip by like it's like 1 frame. So then again we do that and then assign the prediction to last frame. So it's basically so in a sense we use some prior information for every frame to get the estimation. We use some information before that frame also, because if you look at the labels of these valence and arousal, they are like very noisy and they are like it's like real valued labels. So you always have some annotation, some delay or shift. So for example, if you look at the label of a specific frame, it may actually relate to a frame which might be close to that. Okay, so it's not exactly for that label or for that frame. So we use some information before that phase and to estimate the prediction of that frame.
But when you were showing those curves with arousal balance varying, was it on each frame that you're getting prediction?
It's on each frame.
Okay, but when you're computing accuracy in the tables, you do it for a clip.
Yeah, right.
Okay, and you aggregate the predictions, or?
Yeah. It's like within the clip, and then I send it to the last frame of the last frame of the clip.
Okay.
And for recurrent, how to manage the frame rate of audio and video?
Yeah, so that's a good thing. So it's not like end-to-end training, because if you train end-to-end, it's a problem, because audio and visual has different learning dynamics. So it may happen like it's like one modality will learn fast, the other modality will not be able to learn fast. So it's like what I did is like I trained the feature vectors, it's like independently, and for the fusion model I only use the feature vectors, so which is already pre-trained. So I don't retrain the feature vectors. So I train only my fusion model.
And out the frequency of audio and video in recurrent model.
Frequency.
Show the recurrent model.
Yeah. So
Yeah. Mean that when you recurrent the audio for each frame, the spectrum for audio in each frame, I think, is different the frame rate for audio in video different. I
Yeah.
mean that for video 24
Right, right,
frames, yeah, and
Yeah,
for
right.
audio maybe
Yeah,
different. How to manage and aggregate the
Yeah, so that is basically synchronizing the audio and visual. So that I do that even before training the model. So I take care of it in pre-processing step. So in pre-processing, I synchronize the audio and visual modalities so that it will exactly it's like match with each clip. So I take care of that synchronization issue like in pre-processing.
And the last question I have, could you explain more about the J variable in the first?
Yeah,
And
yeah, this one.
and explain for J. I think you have the slides for explaining the J variable.
Yeah. So J is basically it's a joint representation. It's a concatenated version. So what's happening here is like if you look at the model before, the cross-attentional model, we almost have the same thing. But if you look at this matrix, we are doing a cross correlation across audio and visual feature vectors. So that means we are only capturing the inter-modal association. But
in that model, the W is learning form.
It's learning current.
Without any constraint, for example.
Yeah, it doesn't have any constraint. It yeah, it doesn't have any constraint. It's learnable.
Did you check is diverge to zero or infinity training rate? I mean that because you have no constraint on W, what happened in the last training state or last training results? Did you check the base of the W on the?
I haven't exactly did that, but I don't have any specific constraints on W. W is basically it's a matrix which is used to because audio and visual feature vectors are in different spaces. So it's a matrix which is basically used to have some sort of common representation between audio and visual. So
Based on that, you conclude the
yeah,
yeah.
yeah, attention weights. So this is basically the cross correlation across audio and visual feature vectors, and these are my attention weights, which is basically softmax on this like on this matrix. So here the difference is like what we did, like instead of using like HCA here, we use joint representation, which is concatenated audio and visual feature vectors. So that way, like in addition to inter-modal relationships, we also like measure the levels between the same modality. So that's the major difference from the previous model to this one.
And what is the different W, say, CV and WJ?
Yeah, this is like so these the dimensions of XV and CV will be like different because if you look at Z, this is for example, if you have like L clips, and let's say if your dimension is like a dB here, and for joint representation, it will be like L cross dA plus dV. Okay, because we concatenate features, right? So the dimensions of these two are different. So we use these two parameters to bring that to one common dimension so that we can add those two matrices.
It's very hard to draw these diagrams of what I think I was thinking like what is the attention coefficient. So you basically have it in the diagram of XBT, WJB.
Yeah.
And then you already compute the softmax on those.
Yeah, that's true. Right,
And
exactly.
then you have this CV, and then you
Yeah.
CV is the feature which is according to the coefficient
Yeah.
you learned.
Yeah.
And then you have the WCA, which is try to make both of the dimensions the
Yeah.
same, and those are also learnable parameters.
Yeah, right.
Okay. So I just, so what is the two-stage cross-attention?
Yeah, two-stage is basically it's a sort of recursion, like where so if you look at this equation here, okay, so if you look at this equation here, so basically in two-stage, so again we feed that to the same like model, and we add this new one with the actual feature. So the difference between recursion and two stages, in recursion, if you look at this equation, yeah. So in recursion, we add the feature vectors of previous iteration, okay, to current iteration. But in two-stage, what we do, yeah, in two-stage, we add the actual feature vector instead of previous one. We add the actual feature vector, which is let's say to current iteration. So that's the difference between two-stage and recursive.
So the HA was already in the diagram.
Yeah.
It's the final one that you get
Yeah.
there.
Meaning that for calculation, H you want to use attention at the first.
Yeah, right. Yeah. So the major, like the important one is about this one. So this is the important part of this model where it actually so it gives you kind of semantic relevance across like each feature vector. So for example, if you have like L audio features and it's like L media features, it's a kind of correlation across each feature vector across all the media feature vector. So that's the important thing here. So and the attention weights, everything is computed based on that matrix.
So the idea is basically trying to find which one is giving more
Yeah,
information, which model is
yeah,
giving
right,
more
exactly.
information. That is the purpose.
Yeah. So if you look at the matrix, each one will give you like measure of relevance. Like, for example, let's say if you have a clip where we have like very good information like audio or visual, that means you will be having high magnitude for the coefficient. So,
but when you have the joint attention, and then you concatenate the features from both of the modalities, and the attention is basically trying to, the self-attention is also included.
Exactly,
right?
yeah, exactly. That's true. Yeah. It's like within modalities.
I guess it's an attempt to, I guess one functionality that's really important is being able to judge when the modality isn't useful or more important. So
goes to see the same one.
Yeah.
So it balances the attention part, the attention mechanism here balances between how informative faces are and voices are at any given time.
Yeah,
And,
for example, if you
because if somebody starts talking, obviously you're not getting anything from that or if in the case of this lady that is you can't really capture expressions from her face that well, you know, then you can say, well, okay, the face isn't really informative, so we'll focus on the vocal part.
So if you test completely missing one modality.
yeah, we did. Yeah.
See?
Yeah, we did. I didn't put that here. Yeah, but we did that experiment.
And so you'd see if you had like no voice or no vocal expressions here, it would be just a white line, you know, for the A part.
What about the cases that there is a conflict between these two modes? Let's say a person is
Yeah. So I think that is one of the limitation of this approach. Where, for example, if it is entirely, let's say, polarity says like it has like very high valence, and if the modality says it has very low valence. So there are some cases where this model is not able to effectively capture that. So yeah, that is like one of the challenges. Yeah, that's a good question.
Also, the noise, I mean, only the features you are extracting is based on the retained features.
Yeah.
Of no to those kind of images or videos.
Yeah.
So, but still, when you have the ground truth, you also have the aggregated ground truth, and how the ground truth is giving like the same state the last sequence when you compute the loss.
Yeah. Ground truth is basically it's the label of the last frame.
So it's the label of the last frame, but not the aggregated.
Not the aggregated.
Because the prediction you are actually doing is in the last frame.
Yeah.
So it seems like the prediction is not in each frame, but basically
It's kind
with
of
the interval of
yeah, it's a kind of interval of it. Yeah. And that is it is well suited for this application, like especially because, as I said, like it's like real valued like labels. It's not like classification. Like you can say for sure that it's like it's anger or something like that. So you always have some shift in labels because it's really hard to exactly say what is the valence label with the exact real value. So you always have some sort of noise in terms of like in the labels. So to compensate that, we use some prior information, like it's like not exactly relying on that frame, but also some frames before that to have some kind of contextual information.
How is the data labeled? Let's say AffWild2, how is it video tags?
Yeah,
Or is
that
it
they have some
explicit
tools for
per
it.
frame or?
Yeah, they have some tools like, for example, AffWild2, there are around 4 to 5 letters. So where they have some kind of joystick kind of thing. So by looking at the video, they just move the joystick and that it will generate a graph kind of thing. So the same thing will be repeated for 4 to 5 letters and they take exactly it.
So obviously, if you're measuring performance the way you have an arousal valence label, the real value each frame.
Yeah, real value. Yeah, it's like from -1 to +1. So -1 is like for valence is like very sad, and +1 is like very happy. And similarly, for arousal, so -1 is like very calm and quiet, and +1 is like towards it.
So 2-dimension, two values, one
Yeah.
for valence.
Yeah, one for valence, one for arousal.
If you normalize between 0 and 1,
No, I didn't know this. Yeah, I didn't know this.
So in the final layer, we use 10H, right?
Yeah, damage. Yeah, we can, like you were saying that, so that we can have the same interval like -1 to 1.
then it's on the last one.
On the it's like on the output of the last feature vector. Like when you're extracting the feature vector, so the last step we use damage.
But not on the output of the neuron, final neuron. That's just the regression.
Yeah, we use it on the final fully connected layer also. So in the final fully connected layer, we want the labels to be between like -1 to 1. So we use damage for the last fully connected layer. Yeah, for the output.
And did you do any other post process on the labels? Like you didn't normalize?
Yeah,
Any other process?
for RECOLA, I did like mean centering and bias, and you have some bias between the labels and predictions. So for RECOLA, I did, but for AffWild2, I just did like smoothing of the predictions, which means that let's say you got the predictions and you do some kind of temporal smoothing, so that you don't have like sudden transitions. So that's the only thing I guess I did for AffWild2.
And for RECOLA, when you did the pre-processing, did you use the same granularity of labels, like at which the labels were already predicted for the same frequency, or did you do some sort of sampling?
Granularity means like on labels?
Yeah, for labels.
Yeah, it's the same. Like even for RECOLA, it's from -1 to 1.
No, not that. The frequency of labels for each second, 25 labels for ground truth.
Yeah.
And did you do some sort of subsampling when predicting, or did you?
Yeah. I didn't do it for RECOLA because RECOLA is a small data set. But for AffWild2, I did some subsampling because it's a large data set. So I did subsampling for AffWild2 within the clips. But for RECOLA, I didn't do anything because it's very small data set. So if you do that, you will lose like many frames. And yeah.
And lastly, how do you use LSTMs without LSTM concept is to use because how do you use it without in the model?
Yeah. So here what happens is like as you see here, you get a sequence of feature vectors. All right. So you have a sequence, and within the sequence, you have a series of consecutive feature vectors. So we apply LSTM on this part. So within that sequence, within that one, and then you feed that to the fusion model. And same thing we do here. So if you look at this block diagram, you always have a series of feature vectors here and here, here. So it's not just like one feature vector
is with the fusion part and LSTM
yeah. It's like LSTM. So basically the idea is like if you see that previously in the second model in J, we used the joint representation to capture the intra-modal association. So now in this approach, in addition to that, we also explored LSTM. So in order to capture the intra-modal association better. So we want to improve that intra-modal association. We want to capture that better. So in addition to the joint representation, we used LSTMs. So
And it's a recurring.
yeah, it's pretty yeah.
So basically, the idea of LSTM is try to find concatenate the context of temporal.
Yeah, right. Yeah, temporal information. Yeah. And that's why if you look at most of the existing approaches, everyone has used LSTMs. So like in the literature, mostly they use LSTMs. Yeah, because it is very effective in capturing the temporal relationship, like within the model. So that's the reason that we included that one to this model and tried that also.
But there's a cost also, right? So
Yeah.
I think that's the cost.
Yeah, that's true.
I think I guess the way this application is seen right now, it's not necessarily like real time.
Yeah.
It's like a bit of like medical imaging.
Because why I'm asking, so we have projects like H projects where there's also a very serious concern. There are sometimes some age like the age here is like to put something on JSON or JSON or something. And also there are sometimes people like the clients ask for some frame rates, which are we find that very superficial, but this is what people want sometimes. So that's why we always have to go back to either pruning or either restructure the model. That's always the concept in the real world.
But maybe
For this maybe not, but for we have, because I'm thinking of some other.
It could be like a future consideration.
Yeah.
Like for example, you could use this in gaming or anything, right? But I think probably at least in context of Praveen's work wasn't really the first concern. And I mean, there's 3D models in there, and actually, it's good because Praveen was the first one, and we did it kind of as a group, but we participated in this challenge, and we kind of did it at the last second, but it was still kind of competitive. But then we realized what people do with these challenges, it's like several visual backbones in parallel, and it's just the heavy artillery, something you can never apply in practice.
Just to target the performance in terms of accuracy. Or reading about the other side.
Yeah, actually, this one is slightly in terms of complexity, it's less complex and compared to like other existing ones, which is even more complex than the model.
Well, even like if you think, I don't know, like for example, like if you have this model and if you want to put it into, let's say, some small aircraft where you don't have much resources, where you just have to be satisfied with just one annex, where you have just 8 giga, even you don't get the full 8 gigabytes or something. So to feed the model there also, not for the frame rate, but also feed the model also. Even you export it to ONNX, you also have optimized. So that's also something like in each application, there is always this concept.
Yeah. But maybe like only for training, it's bit it takes time. But I think if you go for deployment, that means when you just want to do testing, I think it may be faster.
Yeah,
than it
I mean,
is.
like, that's always the inference. I'm saying like when you try to feed the model
Mhm.
in the memory.
Yeah, okay. Yeah.
You think at SC we could distill this into a small model?
Yeah, right.
He's working on distillation approaches.
Yeah, that's
Like weekly distillation.
That's super.
Okay, well, I don't know if there's no more questions, we can end there. Thanks everyone for coming and thanks Praveen, well done. As I was saying at the beginning, Praveen's like more towards the end of his circuit with PhD, and this I think was a valuable practice, I guess, presenting some of his work and facing some good questions. So thanks for coming out.
Thank you so much for your attention. Thanks for your feedback.
Enjoyed it.